Right. Let's continue. So I'll do like a very similar calculation, but with like a different effect. So this is again fine structure of hydrogen again, but this time I'll introduce something called spin orbit coupling. So what is this effect? Okay, if you let's start with like a classical picture. We have a positive charge, which is the proton, and we have negative charge, which is electron circling around. And this actually also has to do with relativity, right? In relativity, because electron is moving, and if there is like an electric field, a moving object in an electric field is actually going to experience a magnetic field. But we want to introduce this effect in the most economical way. How do we do that? We can go to the frame of the electron. So this is frame of proton. So in the frame of electron, we have electron in the middle, right? And proton is circling around. So this is frame of electron. And a proton circling around is like a current, right? A current loop. And a current loop is going to give magnetic field. And this magnetic field is going to couple to spin. And that's why we call it spin orbit coupling. The orbital motion of electron, which causes it to experience a magnetic field from the proton, and it couples through its spin. So how do we do that? Let's first calculate the, of course, this lecture and the previous lecture. The proper way to do this is you just write down Dirac equation, Lorentz invariance, and all these things, but it's not for this course, right? This course is more like more basic quantum mechanics, and we can get away without doing all of these things with perturbation theory. And what we need to do is like we need to start with like a classical picture and then fix that classical picture at the end. Okay, what is the magnetic field at the center of this loop? Okay, I mean, if you forget, sit down and try to drive Biot-Savart law for like 30 minutes, and at the end of these 30 minutes, you'll lose your appetite for this problem. So that's not the point. I suggest you just go and look at Wikipedia. And magnetic field for a current loop is given by nu 0 I over 2R. And that's all we need. Okay? And what is I? I is plus E over T, and this T is orbital period of electron, because electron orbiting around proton is going to take the same time in its rest frame for the proton to orbit around. That's why I want to use this 2 pi r over t, right? This is total distance divided by total time is equal to v, and I'm going to multiply this with mvr r squared, and mvr is angular momentum. So this one is going to be orbital angular momentum, not vector at the moment. Let's just keep it like that. From here we can find t to be 2 pi r squared m over L, and plug this in here, right? Because I is E plus T. From here, B is going to be nu 0 over 2r plus E divided by T is going to be 2 pi r squared m times L. And if you clean up everything, this is going to be nu 0 over 4 pi. So I got this one, this one, this one. E over m r cube times L. And I want to write it like in a different form, like I want to write it like this. So this is epsilon naught, and I want to use this 1 over c is equal to root nu 0 epsilon naught, right? This is also from E&M. So then this is going to be 1 over 4 pi epsilon naught E over m c squared r cube times L. And to convert it into vector, I just put vector on angular momentum and magnetic field. Good. Now we need to introduce, I think we previously talked about magnetic moment of electron, but let's remember how to derive that. So magnetic dipole moment of electron. Now we are thinking about like electron, right? It has, if you want, it classically rotates around, right? It's like a like self-rotating spinning ball, and that self-rotation is going to give spin, and magnetic moment is going to be due to this. So what is it? Mu classically current times area, right? That's the definition of magnetic moment. And in that case, current is minus E over T, right? This T and the T before are not the same. This T is orbital T, right? So this T is, if you want orbital, this is the time it takes for Earth to take total time around the sun. It's like a year. This T is day and night. This is 1 day. Like this is like spin orbital time. If you want, I can put spin, but it's not important. So this is E over T pi r squared. And I'm going to use exactly the same thing, right? For here, what did we do? So we derive this for orbital motion. For spin, we are just going to change it with S. Good. And from here, magnetic moment becomes minus E over 2 pi r squared m. So this is S, this is pi r squared. You can see radius dependence cancelled. Pi cancelled.
Why did you use the orbital r?
Oh, this is spin. So this is spin. If you want, this r is not orbital r. If you want, this is some other r. But this they cancel anyways. That's a good point. So anyways, the point is that this is going to be minus E over 2ms, and we said there's like so-called gyromagnetic ratio, which is magnetic moment divided by angular momentum, and in the case of electron spin, this becomes minus E over 2m. But we have to remember, these are all classical arguments to convince ourselves with like dimensionful quantities. At the end, right, this is where we need to go to Dirac equation and solve it, and we don't want to do that. The full calculation becomes, so this mu magnetic moment of electron minus E over m. There's like so-called G factor, and I take G factor to be 2. It is not exactly 2, but let's simplify our lives by taking 2. So this is minus E over m times S. Good. I have the magnetic moment, I have the magnetic field. Now I can write the perturbation. So perturbation H is minus mu magnetic moment times magnetic field, right? Compare this with Stark effect. In the case of Stark effect, we had electric dipole moment dotted onto electric field. Very similar effect. But because of magnetic field, we are going to have like a little bit a different calculation here. And this becomes, so this minus, let me just copy this factor here. So this is this is E squared M squared, and I'm going to write this L dot S. Okay, so orbital angular momentum of electron is coupled to spin angular momentum of electron. So that's why we call this spin orbit coupling. And this is also purely a relativistic effect, because for you to have like a magnetic field experienced by the electron, you need to have relativity. Only in relativity you have electric field felt like a magnetic field by a moving charge. Good. Now there's one more actually correction, so let me write the correct form here. So this is H1, and the correct form turns out to be just factor of another 2. So this is 8. But that's not our concern, because this thing, when you learn Dirac equation, this you can derive it much easily. Now the point is not that. Any questions? Now our job is to find the spectrum of this Hamiltonian. H is equal to H naught, which is usual hydrogen atom, plus H1, and let's call this SO, HSO. Any questions? And why do I think this is a little bit different? Because you can see L and S are coupled. So let me call this F of R to shorten the notation. So this thing. Now, in this new term, H and L, what do you think? Do they commute or not? Right? Right? They are not going to commute because of this. So there will be like this F of R term, F of R, right? This is spherically symmetric. I can take it outside the commutator. So this becomes L dot S L. Okay. If you want, from here on, you can just use Einstein summation convention, which becomes easier to calculate things. So this is Li Si. Let's call this as Lj, right? And we should, for example, like this is not a hard calculation, right? I expect everyone to be able to calculate things like this. We need to calculate commutators, and they are not also long, right? How do I calculate this? So this thing is equal to Li Si Lj, which is 0, right? Plus, so this is 0 because L and S are completely independent things. Li Lj Si. What is Li Lj? Exactly. This is the one we should know, right? This is I H bar epsilon I J K L K, and this becomes I H bar epsilon I J K L K S I. You can see this is kind of like a cross product. Therefore, if you just take this out and bring it into like full form, so this L dot S dot L, this becomes, I found, F of R I H bar S cross L, right? Because of this. So the important thing is they don't commute. And if they don't commute, you cannot use L, right? That's not a good basis. Similarly, right, you can also look at this. So this thing with S, and it is going to give you F of R, I, H bar, L cross S. Exactly the same calculation, just L and S are going to be replaced. But we need to find something that commutes. I think it's kind of like we are remembering this addition of angular momentum chapter. So this thing, not only S or L, if I take L plus S, right? So this is going to be this thing plus this. And what is that? 0, right? Because A cross B is equal to minus B cross A, so this is 0. Therefore, this J is a good quantity for our basis. That means if J commutes, JZ also commutes. And let me also not assign you, let me give you this. What about this L dot S L squared? How do we show that? Does it commute or not? What should be the result? So if it was L, we showed they don't commute, but now it is L squared. Yeah, exactly, right? So I write it like L dot L, and I think about this, right? Like L dot S L plus L dot S L L, but we calculated this and we found this to be L cross S. What is L? Okay, this is dot, so this is also dot. What is L dot L cross S? 0, because something, when you take the cross product, it's perpendicular to L, so this is 0. Similarly, so this is L cross S, this is also 0. There are many commutators we need to make sure, but I think they are hopefully not very hard to calculate. Similarly, L dot S commutes with S squared. Exactly the same argument. Therefore, the coupled basis, which was J squared, JZ, L squared, S squared, is the good basis to work with. We have to work with this basis to make calculations. And if you do the calculations in that basis, the first order correlation we need to calculate is SO1 is going to be N, right? J square is going to have J, JZ is going to have MJ, L square is L, and S square is going to S, H, SO1, and the same thing, N, J, okay, let me just write N, J, MJ, L, and S. But we don't have ML or MS. We broke that symmetry, so we have to be in the coupled basis. So let's calculate this. What is this? This is F of R times L dot S. And we know what J square is. J square is, so this is L square plus S square plus 2 L dot S. And this one is going to give us H bar J plus 1. This one is going to give us, okay, this is H bar squared. So this is H bar squared L plus 1. So this one is H bar squared S plus 1. Right, I'm using the same rule over and over again. From there, I find L dot S right? When I take in expectation value, it's going to be h bar squared over 2 j plus 1 minus l plus 1 minus s plus 1. So is there anything I swallowed when I write this? Right? I'm trying to calculate this. Is there something else I need to do here? We spent like entire first lecture to calculate things like that. Anything you see that I should incorporate here? Exactly, FR, right? Who said that? Yes, we need to put FR here. So this is f of r, and this piece is true, but inside, if you look at f of r, we have, you can see we have 1 over r cube, right? We had 1 over r, and then we were like fine, and then we had to calculate 1 over r squared. It gave us like a headache. Now we have to calculate 1 over r cube. And I'll just incorporate here. So this is 1 over r cube. And because this, right, 1 over r doesn't know about spin or orbit or anything. It is just, right, spherically symmetric object. It only knows about n and l, based on what we said in the first hour. And all the other factors, let me just plug it in here. Yeah, let me write them at the end. So this is proportional. And now our job is to find this 1 over r cube. Okay, Griffiths has like some trick for this, I think, which is an overkill. I think I want to use like a trick due to Julian Schwinger, which is a little bit more physical, at least for my taste. So if you think about, right? Whenever you have to calculate something, either you feel desperate and you give up and run away, or you try to find some trick somebody used at some point. So that's what we are going to do. V effective is, in the radial equation, minus e squared over 4 pi epsilon naught 1 over r plus h bar squared over 2m l plus 1 r squared. And he said, okay, the force, the radial force is minus del v effective del r. And he considered the expectation value of this force in a stationary state. So what is the expectation value of force physically, right? We are in a stationary state. What should be the average force? 0, right? If it's not 0, it would not be a stationary state. So this should be 0. But V effective can be, like the force F effective can be calculated. And I found it to be, okay, for some reason I have extra. Oh, okay, there is this additional extra, so minus e squared over 4 pi epsilon naught 1 over r squared plus h bar squared over 2m l plus 1 divided by r cube. And if I take derivative, this one is going to go. And I think it's like this. And if I take the expectation value, so this entire thing, and set it to 0, I find 1 over r cube expectation value is e squared over 4 pi epsilon naught m over h bar squared l plus 1 1 over r squared. And 1 over r squared we calculated in the first hour, so we can use it to deduce 1 over r cube. Okay, that's the trick. Any questions? And once you calculate 1 over r cube, right, you just plug this in here, and then you have the first order perturbation theory. And I can do that, but if you want, I want to write the result and discuss the physics that comes out of that result. So let's write it. So the ESO1 is equal to 1 over mc squared. If you remember, right, this 1 over r and 1 over r squared, we wrote it in terms of En naught, and that's the En naught coming here, En naught squared. So this is n divided by L plus 1. This is this vector, I think. And there is L plus 1/2. This is the L plus 1/2 coming from the calculation of 1 over r squared using Feynman-Hellman theorem. And the second piece is this piece. So this is J plus 1 minus L plus 1. And this piece is, right, spin is just 1/2. So this piece is 1 over 2 times 1 plus 1 over 2 is 3 over 2, which is 3 over 4. So this is minus 3 over 4. And I want to compare this with relativistic correction we found in the first hour. Let me just copy that. So this is the relativistic correction. And okay, did I miss something there? Okay, there's like a parenthesis I swallowed. For some reason this one didn't come out. And for the total, I just sum these. So I want to write E. This is what we call hyperfine, HF, to first order, and it's equal to E1 relativistic correction plus E spin-orbit coupling. And this one is, what did I get? Let me write this like E and 0 squared divided by mc squared. Right, I got this vector, and open like a giant bracket. So this one minus this thing. Let me write it. So this is, so I'll push this 2 inside. So this is minus 2n divided by L plus 1/2. So this minus plus 3 over 2. Good. Let me check. Plus 3 over 2 minus. And okay, we could, spend 10-15 minutes to simplify this, but I want to use Mathematica. I think it actually help with this calculation. If I can open that. Okay, so let's write. Okay, so let me write like this f. Okay, this is like a different function. So this is, let me call this g function, and it depends on n, l, and actually let me write j first. N, j, and l. Right, this is n, j, and l, and it is this function. So So this entire blob, let me write what it is. So this is defined as n divided by L plus 1/2 and L plus 1, and there is another big blob, so this is J plus 1, right? So this is this piece minus L plus 1 minus 3/4, and the last piece is this 2n minus 2n divided by L plus 1/2 and plus lastly this 3/2. Okay, so this is what I define. I use, this is the one I want to show you. I use this full simplify. It actually works pretty good. One of the best things in Mathematica. This is G N L, okay, L, and okay, this is first J and then L, N J L N J L. And here now I need to think about what J can be. So S, okay, what do we do? So J is equal to L plus S, and then J can be what? J can be L minus S, which is 1/2, all the way to L plus 1/2, right? So basically there are two possibilities. J is either L minus 1/2 or L plus 1/2, and I want to substitute that. The substitution is something like this. So this is for J, let's substitute L minus 1 first, minus 1/2. Is this what I did? Yes. And let's see if it's going to simplify. Okay, good. And you can see it's a big blob, but the result is like much nicer. So this is if J is equal to L, which one did I use? L minus 1/2. This E hyperfine 1 is equal to this factor times 3/2 minus 2n over L, but L is not a good number. I need to write everything in terms of J. So this is L, but I will write a J plus 1/2. And the other possibility is exactly the same thing. So, but this is plus. You can see this is now exactly the same form, but L plus 1. So if this is J is equal to L plus 1/2, we have exactly the same thing, except so this is 2n over L plus 1, L plus 1. But L is not good, right? Whenever I see L, I need to write J minus 1/2. J minus 1/2 plus 1 is J plus 1/2. Right? So it's the same formula. And if L is equal to 0, what is spin-orbit coupling in the case of L is equal to 0? Right? If I have L dot S is 0 because there is no orbit, so no spin orbit. And it turns out, right, when you do it like this, it kind of depends on L, and the result should not depend on L, right? Because L is not a good quantum number, and we should not have something L dependent at the end. There is something called Darwin term, or in the German, I think it's something called Zitterbewegung. So this is called jitter motion. due to finite size of electron, right? Electron is like a point particle, but if you look at it close enough, it's actually some fuzzy particle, and if you take into account, it's going to give a term like del squared V, right? Coulomb potentials del squared. It's a little bit more involved, but we don't have to calculate that. If we calculate that term, entire hyperfine state becomes exactly this, and no L dependence. Okay. So it basically fixes this special case, and at the end we have one unified result to first order perturbation theory. Good. And let me write the result, and then let's discuss and finish it there. So in total, energy En divided by, let me write it like mc squared, happens to be minus 1/2 alpha squared over n squared. This is 13.6 usual term, plus 1 over 4 alpha to the fourth, 1 over n to the 4, and 3 over 2 minus 2n over j plus 1/2 plus dot dot dot. And we have to remember this alpha is 1 over 137, and we are talking about a very small correction here. Good. Any questions? Okay, now what is the physics, right? Is this even relevant? This is actually quite relevant, and you can see it even in, like, for example, hydrogen. Let me just give you the experimental upshot and then close it there. If you consider Balmer line, which is n is equal to 3 to n is equal to 2 transition, which is like a red light, right? If your resolution is not good enough, you have like a single line here, like this. So this is n is equal to 3. Let's say this is n is equal to 2. So this is n is equal to 3, and n is equal to 2. And you have one transition like this. Put like an arrow. And you are supposed to see one single line. But as soon as you take this spin orbit coupling into account, right? So n is equal to 3, what can we have? L can be, okay, let's write here because I need here for diagram. L can be 0, 1, 2, right? It goes all the way to n minus 1. And S is 1/2, therefore J can be 1/2, right? 0 plus 1/2 is 1/2. 1 and 1/2 can have 1/2 or 3 over half. And 2 and 1/2 is going to give us either 3/2 or 5/2. Right? And splitting is, you can see, J dependent. Therefore, this is going to split into 3. So there'll be 1, 2, 3 line. And here, so this is L can be 0 or 1. J can be 1/2. 1 minus 1/2 is 1/2, or 3/2. And there is nothing else. So this line is going to split into 2. Something like that. And these are still Balmer lines, but like this single line in the emission spectrum is going to split into what? So you can come from here, you can come from here, or you can come from here, right? 3 lines to this transition, or you can come to here, here, and here. So this single expected line splits into 1, 2, 3, 4, 5, 6 lines due to spin orbit coupling. And you can actually see it with your eyes if you do the experiment. Or if you Google hydrogen spectrum Balmer line, I think it's going to show a couple of splittings.
John,
Yes.
there's selection rule as well, right?
Yes, absolutely. And these are all consistent with selection rules. Yes. And okay, think about selection rules. I didn't calculate it so much, but exercise, consider so-called dipole selection rules. That's a very good point. What was it? So we are supposed to have delta L is equal to plus or minus 1. And we also need to have this delta J is equal to 0, plus or minus 1. And consider if these transitions are consistent with that. That's a very good point. Good. Any questions? All right. Thank you. I'll see you guys on Friday.